Hi everyone, thank you for coming. Today we have a special guest that is visiting us. I will introduce you to Robert Taylor. He's a really well-known researcher. He's a professor at the University of New South Wales in Australia. And he will present us today's result of his research related with solar thermal technologies, also electrical in between. So he was invited to Chile for the Universidad Técnica Federico Santa María, a project that is in community with all of the branches that are in the presentation. But I wasn't with God on Tuesday, and we thought maybe it's a good opportunity that we can visit us. This is the presentation that we will perform today. So thanks, Robert, for coming and for your time. You have the video.
All right. Thanks for the introduction, and thanks for inviting me, and thanks to all of you for coming on last minute notice. I think this was advertised on Wednesday, and somehow you came here on Friday. So thanks for attending. I'm just going to tell you a little bit about some of the work that I've been doing at my university over the past few years that relates to this FOVI project that we've got in collaboration with all these universities, and what basically brought me here to Chile. And basically it's thinking about how to use my part of the project, I guess, is thinking about some of the ways that we can use solar energy to do something useful, like create fuels or maybe store some energy for later. And I think that there's a lot of similarities between Australia and China, and Chile, in terms of, I just been to China before I came here, in terms of some of the parts of our economy. So Australia and Chile both are a lot of mining industry, and that requires a lot of energy. Also, there's some very good solar resources. In fact, I think Chile maybe has higher resources even than Australia in some parts. So there's a lot of similarities, and I think some of the similar opportunities as well for utilizing those solar resources. But before I talk about some of the actual research, I thought I would introduce my university. So we're kind of a top-ranked university in the world according to the QS rankings, number 19, which is pretty high ranking, I guess. And we're located kind of in the southeastern part of the country. So it's that's the whole country. Zooming in, we're in Sydney, and then zooming in further, we're pretty close to the ocean there. So it's a pretty nice destination, but it is a city campus. So it's not a very large campus, and we don't have a lot of space. I would like to do some really large scale stuff, but I'm kind of limited to what I can do on rooftops. So I have some solar energy outdoor experimental work, but it's limited to what we can fit in a rooftop space. So that's what we have. Also, we're celebrating 75 years at my university. So we're not that old, but it's old for Australia because Australia is kind of a new country, I guess, in terms of the Western civilization part of it. It's got a long history of native people, of course, but and I work inside the mechanical and manufacturing engineering department, which is quite large department, one of the larger of our engineering departments. So I think we're number 3 maybe in terms of, there's nine departments in engineering, and mechanical engineering is probably the 3rd biggest. We have about 2,500 students and about 40 to 45 academic faculty members. And we teach basically 4 major programs: mechanical engineering, aerospace, manufacturing and robotics, and mechatronics. And then we have a small program that's growing for nuclear engineering that we're going to develop. In terms of the research at my university, we bring in about $10 million a year, Australian dollars a year, which is about 7 million US. And we publish something like 350 to 400 journal papers per year just in my department. So that's pretty good from 45 academic staff. About 1 journal paper per day on average is what we're producing. It also turns out I'm the deputy head of school, so I'm sort of in charge of all this organizing the research for our department. So I have to keep track of those numbers and statistics. We're also ranked highly in terms of our different subjects. So these are the subject rankings. So we're ranked somewhere in the top 50, 40 to 60, I guess, on average in terms of those mechanical engineering subjects. So that's pretty good. And so within Australia, we're probably number one for the mechanical engineering. The way that our program works, which is interesting, I think, to compare to the Chilean system, which I heard somewhere used to be 6, 7, 10 years sometimes if people get delayed, where our degrees are 4-year degrees. Okay, and the first couple years are kind of fundamentals, and then people specialize within those different majors that I discussed. And so that's how it works. And we try to get students as much kind of hands-on experiences as possible, especially for mechanical engineering, where you should be doing some hands-on work, I think. And the way that we do that is with kind of big projects. So we have a lot of these student projects. So just a few of the pictures there. There's a project now to build a nuclear fusion reactor, which is the kind of the top left thing. There's a rocketry team. We have students building kind of robots, mechatronics students. There's some flight simulator thing, and all the students in the aerospace eventually go and do some flight training. And we have, it's called Design, Build, Fly airplane team, a solar car, and a Formula One racing car. And just the thing that I'm involved in most is with this solar car. So we had a solar car race last year. I went along with the students. We camp out in the outback of Australia. It took about 5 days to go from the north of Australia to the south of Australia. And it turned out we got first place in our category, which is this cruiser class car. You can't see it here, but there's solar panels on the top of the car. But mostly this car, because it takes passengers and it's kind of a larger, more like a regular car than those original solar cars. It's more like an electric vehicle, basically. But it does have solar to supplement what you get from the electricity off the grid. And of course, that's the famous rock in Australia called Uluru. Probably seen it before, that red rock. So it goes through the outback of Australia. Nearby this red rock is sort of there in the middle by Alice Springs. So that's a pretty fun project. The students build that themselves. They do all the carbon fiber. They design all the parts, 3D printing some things, doing all the manufacturing as much as possible on campus and sometimes with the partners. And then in terms of our research, we have a lot of partnerships with lots of industry partners. So Australia doesn't have wonderful industry in terms of doing research and development, but we do have a little bit. And there's a few companies that are interested to do things which we partner with to try to advance their technologies. But, you know, I think probably some similarities with Chile industry, that people just want to dig stuff out of the ground and make money, and they don't want to do a whole lot of development because it's easier to just, you know, do things quickly. And so it is a bit of a challenge to get industry involved in research, but we do manage to get quite a bit, I think, from different things. So just a few examples. There's some work going on to convert large diesel engines to run on hydrogen, because we think hydrogen could be one of the future fuels. And it's, of course, carbon neutral fuel if you produce the hydrogen in a green way with no carbon inputs. You can store the hydrogen in big tanks. So carbon fiber tanks is another thing that our department does. There's some work with solar boats, and then a few other just industry applications, including kind of health things. So this is a sleep apnea machine and some hearing aids and stuff company with that. And then, yeah, anyway, lots of different projects. But what I mostly wanted to focus on today was solar energy. And that's my area of research. And my university is very famous for solar energy. So especially with the photovoltaics department, they set a lot of world records in terms of the photovoltaic cell efficiencies. So like basically back in the late 80s, early 90s, almost all the silicon photovoltaic record efficiencies came from my university. But there's been some more recent things that just in the last few years on different types of solar technologies where we're still setting world records. And in fact, almost all the researchers that were there back then, there's a guy named Martin Green, who's very famous, are still at the university, still supervising PhD students and doing stuff like that. And what people may not know about so much, it's not as famous, is that almost that whole time there's been solar thermal research, which is more like my area. There's been a solar thermal lab since the 80s there. And we have rooftop testing capability. And we've tested all kinds of technologies from kind of low temperature things, from making heat that's at low temperature, like hot water, all the way up to kind of high temperature kind of materials processing things, which I'll show a little bit about later. So it's kind of a long history of solar energy research, probably one of the most famous things at the university. All right, so the solar opportunity, and the reason why I'm excited about solar energy, and hopefully after this, if you're not already, you'll be excited about solar energy, is that it's a huge resource. It's a huge resource, something about 10,000 times our global energy demand is available from solar resources right now. So we don't need to harvest even 1% of that resource, and we could grow our economy even more. Which is pretty interesting to think about, just that fundamental thing, because if you think about fossil fuels, there's not a whole lot more room for growth. If anything, we need to stop using that energy because it's harming our planet. But solar energy, we could keep growing and growing and growing for generations and keep harvesting more and more of that resource. We got 10,000 times more there to work with, okay? And then in terms of where those resources are, you guys here in Chile are very lucky. You have such wonderful resources. Good place for concentrating solar thermal plants, solar PV plants, and same thing in Australia. But there is one challenge, and the challenge is the people don't necessarily like to live in the places where there's the best solar resources, because it's hot, dry, no water, it's hard to do agriculture. And so I think even in Chile, this northern part of the country is not very populated. Most of the people are down here by Santiago. So you're going to have to think about how to get that solar resource to the people, because that's where we're going to consume it. And definitely in Australia, this part of the country, all that red, looks so good, but nobody lives there. That's where our solar car race went through. And I can tell you there's nobody there. You can look, if your car breaks down in the middle of the country, there's no help coming for you. This is just a population density map. So again, the people live here. You can see the density of the population is along the eastern seaboard. And a lot of people live up in Asia as well. And so one of the ideas, I suppose, for Australia is to somehow take those solar resources, put them into something that can then be exported off to where not just the people living in Australia, but the people living in Japan and Korea and all the Southeast Asia countries, right? And I think, probably can make a similar case in Chile that if it's a mining economy, why not mine the solar resources, put them into something that you can export to people that, maybe could get things up into other population centers. Okay, so I think there's some good opportunities for solar resources if we can find good ways to embed that energy of the sun into things besides just electricity. Most people, whenever they think of solar energy, they think of electricity. But if you can put it embed into some of the minerals processing steps, take a lot of energy. If you can embed it in there, that's like exporting your solar energy. If you can store it in some kind of fuels. So this last week I was at a conference, a lot of the talk was on hydrogen and ammonia. And if you can put solar energy in and produce those fuels, you can then transport those fuels. And then you can sell those somewhere else. So they're thinking, again, Australia is thinking to make hydrogen and transport it up to Korea and Japan. I think that's a great idea, but it takes a lot of research and a lot of science development to make that stuff happen. So I'll just tell you next about some of the work that I've been doing in those kind of areas, and sort of maybe some of the collaborations that I think could be good between Australia and Chile. So we had this project for the past few years. It's sort of finished now, but our idea was to use some biomass that's readily available in Australia, which is sugar. I think another product in Chile is a sugar industry, right? In Australia, we have a big food and beverage industry, which takes the sugar in, and then there's a lot of waste sugar in their waste streams from these food and beverage plants. And of course, we have solar resources. So if you can take that sugar biomass, sucrose, and solar energy, and then eventually turn it into something that's more valuable, that can be transported as a fuel, then you've got something there that's interesting. And so this project was trying to figure out the best way to do that. What we came up with was a two-step process. The first step is a thermal process. Well, before that, you got to collect the sunlight. So we did a little bit of development of the solar collector. But then there's a thermal step and then electric step. And both, of course, the electric step could be powered by photovoltaics. And we thought it would be easier to control the processes if we did that. So we take the sugar biomass into the thermal step, and you sort of crack it, I guess, into this intermediary chemical called 5-HMF. And then take that 5-HMF and put it through a flow electrolyzer cell and turn it into hydrogen, which was one of the main outputs for this Australian renewable energy project. But also we can make another chemical called FDCA, which is a valuable sort of chemical precursor for lots of chemical products. And it turns out that FDCA is actually worth quite a bit more than hydrogen. So there's some goals in Australia for the hydrogen to end up being $2 a kilogram. But this FDCA is over $100 per kilogram. So it's actually a lot more valuable to be making that. So my argument at the end of this project was, why do we even bother with the hydrogen? We should just make FDCA as much as we can. But hydrogen's what we wanted, and that was the kind of the goal of the project. So we managed to do that. And after a lot of prototyping and researching, we tried to make a whole system which worked together and was totally off-grid. So it's on this cart. That's the final kind of product of the project, was this cart which has the PV module and the thermal module, and then some pumps and some things down below, and some water treatment things down there. And all of it worked together, and it had a continuous kind of flow to go from sugar, which we actually just use Coca-Cola as the input, or apple juice. We tried both, same kind of stuff, just sugar. And the output was hydrogen and this FDCA. Okay. And there's some papers I'll be citing along the way. So I'll just take you through just a little bit about how the design of each of those parts. So the first part of it, which is sort of my area mostly, is the solar stuff. And what we realized was, to do this thermal process, you have to get up to kind of a medium temperature. About 150 degrees is a good temperature to get that thermochemical reaction to work. And so to get to 150 degrees, you need a little bit of tracking and a little bit of concentration of the sunlight. But we didn't like the idea of just using standard stuff where you have to do 2-axis tracking, because it would be kind of expensive and hard to integrate. So we went for this kind of unique design, which we called a winged CPC. And I'll just explain a little bit about it. So it has these, well, first I should say the CPC is a compound parabolic concentrator. And the advantage of a CPC is that within a certain acceptance angle, all the light that comes in from any angles, as you know, the sun moves through the sky, right? And as long as it's within those acceptance angles of the CPC, it'll bounce around in these mirrors and finally make it to the tube receiver at the end. Okay. So you can see some ray tracing results here, where we simulate the sun in a model, right, and send some rays down, and it bounces off the wall and then bounces over and hits the tube and then gets absorbed. And it doesn't matter, as long as it's within that acceptance angle, it still works. And we wanted to do a little bit better than that. So we put these, just a mirror, a flat mirror on the side, and it has a wing on it. And then the wing can bounce the light into the CPC and then get it back into the tube. So it's a way to just get a lot more solar energy into the tube. If you just put the tube by itself, you won't capture very much. So it's this kind of a special design we tried, and you have to figure out, this laser pointer is not working, but you have to figure out the ideal angle for these wings throughout the day and how to track and what's tilt angle and everything. And that was quite a bit of optical design work in there. Then the tube is a vacuum tube. Do you guys know anything about vacuum tubes? Well, anyway, there's a product that I saw them all around rooftops around here, but evacuated tube collectors work because they're very good at holding the radiation, absorbing the radiation in the first place, and then keeping it inside. So the vacuum insulation stops the conductive and convective heat losses. And then there's a special coating on the inside of it, which is radiative selective surface. So it absorbs the light well, but doesn't emit the radiation. So so these, oh, sorry. Yeah, that'd be good. Does the pointer work? Okay, yeah. Okay, so that vacuum tube was provided by our industry partner who makes the vacuum tubes. They make very long, more than 1 meter vacuum tubes for about $1 US per tube. So it's pretty low cost, even though it's got a vacuum and it's got this selective surface, which is a kind of a thin film deposition process. And so it's pretty good for getting to high temperatures because it's good for the radiation properties. So anyway, once you concentrate the light and you get in onto this vacuum tube receiver, then you can get to high temperature. And we wanted 150 degrees. So then the next step was doing the chemical testing, thermochemical testing. So we put this thing out in the sun. So that's kind of what it looks like now. So you see blue everywhere here. That's the color of that selective surface in the tube. So if you look down from straight above, it looks huge, but it's really just a small tube that you're seeing and all the light that is going into that tube. And then we put the sugary biomass, the Coca-Cola, into the tube. And unfortunately, one of the key things about this is its acid catalysis process. So you have to put a pretty low pH in there for this process to work well, or at least to get to the lower temperatures. So it's a pretty strong acid. Also, it needs to be pressurized because we're going above 100 degrees Celsius and it's a aqueous Coca-Cola will boil normally. So we put it at 5 bars pressure. So anyway, we thought we could just do that inside the tube, and the manufacturer said you could just pressurize the tube, but we were cracking some of our tubes. And so we had to redesign it a bit with a titanium U-tube, which is holds the pressure on the inside. But anyway, we did some tests. It turns out that over time, of course, the thing heats up and you go through lots of chemical reactions. So you actually have to stop the process somewhere along the way at the right temperature and the right amount of time to get the maximum amount of this 5-HMF, which was our target product. But anyway, whenever we did it, kind of the best result, it was about 25% efficiency, thermal efficiency, and we could get a yield of about 22% from that system. So there's probably room for improvement there, especially for the yield. I think you could get the yield up quite a bit. But the thermal efficiency, 25%, that's a little bit low. It's not bad for this temperature, but that's of course accounting for the whole solar resource is the denominator of the efficiency, and then the useful heat extracted is the numerator. So yeah, anyway, that's the result. The next step, then once we have what we want, which is this 5-HMF, we can flow those products into this flow electrolyzer cell. And then inside of that, if you want to be off grid, it turns out it's an electrical engineering challenge where you got to get a match between the photovoltaic current and voltage that you're getting from the photovoltaic cells and these kind of electrolyzer cells. And the electrolyzer cells would like to have very high current. And photovoltaic modules kind of normally give you very high voltage. So what you have to do to get a closer match is put the PV modules in parallel, and then put the electrolyzers in series. And if you do that, you can kind of get it to be pretty close, because you want to get kind of towards the maximum power point of the photovoltaic modules. And you also want to operate, you got to get enough current into these cells to make them work. And also I should say, whenever you put in that 5 HMF, it's actually a lot lower energy, about 25% less energy than just trying to split water by itself. So it gives you, if there's an advantage to doing this, and it's a big energy savings, I guess, to have that intermediate chemical in there. Okay, so anyways, that's the design for that. That of course doesn't, the parts of that can be like these stacks can be down below. They don't need to be in the sun, just the PV module needs to be in the sun. So it's kind of large and a big cart, but you could imagine making a nice product that was, you know, all integrated, and just the solar was out on the top, and then everything else was all inside of a controlled cart for environmental control, because there's a lot of electricity in there and stuff. We only tested on sunny days. If you were out in the rain or something, you'd need to be protected from the wet weather. So the overall results of this is basically we built this kind of prototype system, which was about 2 square meters, 300 watts of thermal input, 100 watts of PV electricity, and then it all was matching and giving a nice kind of continuous product. There's a paper on it if you want to know more details about it. But it turns out, you know, it's pretty interesting engineering design that we didn't think of all the stuff whenever we started. We just thought, oh, this will work. But actually, when you get into the details of stuff like this, you have to do a lot of redesigns and a lot of you know, sort of playing around with the different configurations, and operational conditions are very important. The overall solar to hydrogen efficiency was about 10%. Which doesn't sound that high, but that's pretty good for off-grid system, I think. And also that's just the solar to hydrogen. We still have this FDCA, which is another product, and that's kind of a valuable product as well. So in terms of the economics, we did a little bit of economic analysis, which I guess is in this paper. That FDCA is the most valuable thing. You might also get paid to take that waste, sucrose, because it's a trade waste that they have to pay to dispose of. Of course, all the components of the design could theoretically be manufactured at pretty low cost. So there's an ongoing project there to try to make it a smaller, more kind of compact product, and it's continuing with some of the partners. Okay, so you may have noticed the way that system worked was the thermal system was separated from the PV. Some of my work, or a good amount of my work over the last few years, has been trying to bring those things together and make the PV and the thermal integrated. And so I'll probably talk about a few ways that could work next. So why would you want to do this? Well, the first reason is that if you think about a PV module, I don't know if any of you guys know much about photovoltaics, there's a certain band gap. So for silicon, 1.1 micrometers is the band gap. So anything that's lower, any of the photons that are lower energy, which is the infrared parts of the spectrum, they won't do anything for you for your silicon PV module. And they just kind of, if they get absorbed, they just turn to heat. Then for the short wavelength stuff, so like the blue light and the high and the purple light, it has way too much energy for that band gap. So you actually, you know, when you get to blue light, you actually have 3 times the amount of energy that you need in that photon to make the electron jump across to the conduction band, right? And so if it's 3 times as much, only 1 unit of the or only one part of the energy is going to creating electricity, the other two parts turn to heat in process thermalization. So basically, only the red part of this curve is good for the PV. The rest of the solar spectrum, which is landing on the ground, just turns to heat anyways. So that's 80% of the solar energy that's landing on a PV module is just turning to heat. So why not capture that heat? So that's kind of theoretical argument. And where does it make sense? Well, it makes sense in an industrial process where you have a very high energy demand per square meter, and then you have a limited rooftop amount of square meters. It also makes sense in a large building where you have like many levels, and again you have a high energy demand per square meter of footprint area and only so much rooftop space. So if we want to get to kind of like net zero, we're going to have to do better than 20% efficiency from PV, I think, for at least in terms of rooftop generation. And so anyway, so that's the basic argument. And then of course we need heat for many processes. So we need heat to heat and cool buildings. We need heat for hot water. We need heat for industrial processes. And we need heat at a bunch of different levels. So there's a bunch of different PVT technologies that might fit into those niches, I guess. So anyway, so one of the other parts of that same project was we tried to integrate it all together and do the same sort of thing. And in this case, what we did, one of the options that we tried was depositing some PV that's kind of flexible and transparent PV onto those wings of that winged optical device. And so that way, what you do is you take out those parts of the spectrum that are good for the PV, you take them out first, and then the rest goes down into the reflector and gets reflected back onto that tube. And then you can still have concentrated thermal. And the nice thing is this PV is a little bit away from the hot temperatures of the thermal, so it doesn't get heated. So it's operating at its normal kind of operation temperature, and it's not connected in terms of thermal contact between the PV and the thermal receiver. And so we did some tests with that. We're still able to get about 100 watts, I guess, from this kind of system, and then still trying to get 150 degrees Celsius to run that same sugar cracking process. And the PV part, by the way, is like this kind of thin film stack thing that's developed by another researcher, Xiaojing Hao at my university. And of course, we can still drive with that electricity, we can still drive these electrolyzer cells, which we test at UNSW. And of course, you have choice of the design of those, how big you want them to be and everything. So that's one way. So one way is you can take the electricity out first and then reflect the light onto a thermal collector. That's one kind of PVT. Another type of PVT, which I've spent a few years doing, is you take the thermal first and then send the rest to the PV. And I think both of the ideas are pretty interesting. And both of them follow this, that you have the same idea here where the PV efficiency is a function of temperature. So if you somehow have the two connected, the PV and the thermal, then as you heat up the thermal part and get a more valuable output from the thermal, you hurt your PV. So it makes sense for both of these designs, I think, to split them up. And that way you can get a good high thermodynamic quality thermal output. Maybe 150 Celsius would be a good target. And you can also still keep your PV operating at its high efficiency. So another idea, which I had a few PhD students doing, was developing nanofluids, which are special, and they absorb just the parts that are not necessary for the PV. So they absorb the infrared parts and the short wavelength parts, and then they transmit sort of the yellow, the red and maybe a little bit of the yellow light through to the PV. Of course, we tested lots of, because it was basic science, we tested lots of different particles, lots of different fluids, and even different kinds of PV cells, because different PV cells have different band gaps. So you could design these things for different ways. But I'll just show you one of the designs, which I thought was kind of the most promising. And it turned out to basically be like these candies, this M&M's candies. And the reason that it had to, or the reason I was kind of like that is we wanted a very special shape and aspect ratio and size of silver, because silver has an interesting spectrum. Whenever you make a nanoparticle out of it, you're kind of confining the electrons in the nanoscale, and then you get different absorption to what you would get normally from a bulk silver. So bulk silver looks kind of, metallic, the color of silver, I guess. But when you make it nano, you can get all these different colors. But the problem is if you make let's say a nano disk, which is what we wanted, over time, if you heat that disk, it's going to turn into a sphere. And silver actually melts in the nano size. It actually melts at below 100 degrees Celsius, which is kind of weird, but it does. And it certainly would form into a sphere to reduce surface energy. So we want to keep it as this weird disk that we designed. And the only way to do that was to put this shell on it. And so the shell is made of silica. And it's a lot like just basically the same idea as these chocolates, where if you just had a bunch of chocolates and you put them out in the sun, they're going to melt and stick together, and then they're not little pieces of chocolate, they're goo, I guess. Same thing would happen in here. But if we put that shell on it, then they stay separated, they keep their shape and their size, and most importantly, they keep their optical properties, which is very important for transmitting the right spectrum. Okay, so is any of you guys chemical engineers? No. All right, that makes it easier. Well, anyway, the way that you make these things, you start with it's a precipitation reaction. So you start with a silver source, and you have kind of a precipitation reaction with citric acid and this PSSS. And you basically, you screen off some of the planes. So you screen off some of the planes, and you just make that seed grow in certain dimensions, and then you can get a disc. So that's the way we grow them. As they grow, they change color. So it's pretty kind of beautiful colors. So if you start with I can't remember, the seeds are kind of a yellow color, and then as they get larger and larger, they blue shift. All right, and eventually you can get purple. So you can see how you could definitely control the transmission and the absorption of the thing, and you could think about mixing different sizes and shapes. And so there was a good PhD student that came from material science that was working on developing these, and you've got to stop the reaction at the perfect part. And it turns out that you want something that's kind of pinkish in color in the end. And so we started with just little batches of these things, and then eventually scaled it up and made several liters of this stuff. Of course, a lot of science along the way as to the temperatures and the times and the concentration of the reactants and everything. But eventually we got something that we thought was good enough that we could test it out in the sun. And what we did was we made a small, it's a PVT system, prototype system, where maybe a little bit hard to tell what's going on, but there's a flat glass channel, and this nanofluid flows through that channel, and then the stuff that's transmitted after that thermal receiver goes down onto these PV cells, which are down here. PV cells that are down there. And of course, because I said we wanted to get to higher temperature, we had a Fresnel lens at the top to focus the light. So this type of Fresnel lens is a linear focusing one. So it just focuses the light down onto kind of a line, and that's what it looks like under the sun. So the illumination line is very bright, probably 10 times solar energy focused on the thermal collector, and then the PV cells are underneath. Again, a lot of design going into there. We had to develop some of our own little electronics to do the IV testing of the PV cells. It turns out you got to cool the PV cells because they're concentrated light on them, and you don't want them to get too hot. Efficiency goes down. And yeah, just designing this whole thing, tracking out in the sun. But anyways, good for a couple PhDs to develop that system and test it. And we got very good efficiencies out of that. And most importantly, we proved that we could do the thing, which is split the spectrum very well, make a nice fluid that gives you 80% of what you want gets transmitted and 80% of what you wanted to absorb gets absorbed. So, all right. But the trouble is, it's a bit costly, right? Especially whenever you start thinking about the PV in here with specially made PV cells. They're very high efficiency, but you don't, if you go to the solar company, you can't really ask a solar company to make you that line, that PV in a line, a bunch of cells in a line. What they actually make is big rectangular modules, and those are getting very cheap. These PV line things are specially made and a few $100s per watt to get it specially made PV cell, but US dollars per watt. But a big module now is like getting down to 20 cents a watt. It's very, very cheap. So, so that was a big contributor to the cost. So the next bit of work, which is ongoing now with a master's student, is to kind of use the same, almost exact same technology, although maybe make a spot focus, so get even higher concentration ratio instead of a linear focus, and then spread the light back out so that it's one sun again for the PV module. And then we can use a regular PV module, 20 cents a watt, and we can get an even higher temperature from the fluid. So we're designing this little receiver, which is going to be kind of a circular receiver. And it turns out, I think we want to mix up that fluid and make it sort of all the same temperature. We don't want any hot zones in there, and we definitely don't want to crack our window or have a lot of heat loss. So so then there's a bunch of choices that you can have in terms of a design choices of if the inlet, okay, so if you take the fluid and you flow it straight through the middle of a circle and the sunlight's coming in there, what happens is you get some dead zones on the side, and those are hotter than the other parts, and it's not very good mixing. If you put it 90 degrees, then you're going to get some swirling and some mixing, which is good. But it doesn't always do what you think it's going to do. And we've been doing some CFD simulations, computational fluid dynamic simulations. Another thing that's important is the angle of the inlet, and you want the inlet to go and hit the window first and take away the hot part of the fluid that can get stuck by the window. And okay, so what we've been doing so far is just designing this thing, doing a bit of that ray tracing, so we know exactly what's the irradiance profile on the receiver and the intensity of the light, and then we can use that as the input for the thermal model. So the thermal model, this is just some CFD results where we basically, our metric of goodness is what percentage of the receiver is a dead zone. And it turns out that as long as you do a good job of directing the flow, you can get a pretty low percentage volume dead zone. So we want to get down below, definitely below 10% as a dead zone, I guess. So anyway, we've been playing around with different designs and trying to come up with some optimum. And then the next step, we're building the rig to test this. This is ongoing work, I guess. We haven't actually got the test results yet, but we're building a very similar rig to what I showed earlier with the concentrator, and we're going to put this in the receiver, and then down below that is a PV module. Okay, one last project idea that we worked on, another PhD student, still PVT, but this time the idea for the T, for the thermal, is to do some minerals processing. So we had a project where we were trying to do a big minerals processing industry in Australia is making aluminium. And you start out with bauxite, which is kind of like the raw ore, and then you turn it into alumina. And in that process is a high temperature step, a calcination step, which needs like 700 degrees Celsius. And all you're really doing is stripping out some of the hydrogen out of there and turning the bauxite into alumina. And there's a lot of interesting parts of that process, but one of the things is if you go very fast and you have a high heating rate, you can make certain phases of alumina which are more desirable. If you go kind of slow, you get on another track and you get less desirable phases of alumina. So we're after this kind of gamma phase alumina, not the alpha phase. And anyway, there's a lot of ways to do it. So traditionally, of course, the way that they do that calcination step is with gas, and they burn gas, and they can get very high heating rates. But if you use concentrated sunlight with a big, say, Fresnel lens, you can get the same kind of heating rates. So we did some testing just with thermal receiver. So you have a Fresnel lens focusing down into a small spot window. The receiver looks almost the same as the receiver I just showed. So it's got some stainless steel, and you put this powder inside of there, and then you can basically get that calcination reaction to occur. The problem though with it is if you directly irradiate this powder, I don't know if anybody's seen alumina powder, but it's white, so it's very scattering. So it's kind of similar thing, and made me think about PVT, because what's scattering is some of the short wavelength stuff that might be good. And you see with this white light, a lot of it's the PV, stuff that could be used by the PV. And the infrared and the stuff that your eye can't see is actually still getting absorbed. So we did quite a bit of property analysis of the materials, and it turns out that alumina is only absorbing, if you directly irradiate it, it's only absorbing about 16% of the sunlight, it changes phase, of course, so it changes throughout the process which parts of the spectrum it's absorbing. But it's pretty good absorbing the long wavelengths and a little bit of the short wavelengths. So this middle part is kind of like available for a PV system. So then we tried to figure out, well, how can we design a PV system that could go in front of this and take its electricity first, and then send the thermal and then still send the thermal energy off to this alumina. So we came down with we found some transparent, kind of semi-transparent PV modules that could just go in front of the Fresnel lens or behind the Fresnel lens, and they would take out their electricity first. And actually, the spectrum matches really well. So this cadmium telluride, turns out it absorbs stuff that's not really used by the alumina. So we've been doing PV tests. And of course, with PV tests, you're looking at the current and the voltage and trying to figure out the max power point and all that stuff. And we did two configurations, one where we put the cadmium telluride cells above the lens and one below the lens. And if you do above the lens, it's just like it's in the normal sun. So cadmium telluride is not so efficient of a PV module, but it still gets 7% efficiency, which is not bad considering it still transmits a lot of the light that can then be used later. If you put it below the lens, it gets kind of non-uniform irradiance, and there's some of the light is lost by the lens, of course. So you really hurt your PV efficiency. So it turns out that that's not a good configuration. I think just put the PV above the lens was the best configuration. And then in terms of what happens to the thermal reaction afterwards, we still get pretty good heating. So the above the lens configuration, we could still heat it up to maybe 450, I guess, 450 Celsius. And then the below the lens configuration, it was able to get to 650. So unfortunately, at least with our setup, we weren't able to get to that 700 calcination step, but it's not far away. So with some supplemental heating or maybe a little bit better design, we could still do that calcination step and get 7% efficiency from the PV cells. So that's a little bit ongoing work there too. But I think some part of the aluminium processing is going to eventually need to be solarized. And I think the PVT might be an interesting way to do it. In terms of the PV efficiency, the best design 7.5%, and then the thermal efficiency is somewhere near 10%. So I guess you could add those two together and say 17% of the light is turned into to useful electricity or into the thermal reaction. By the way, the electricity is going to be used later whenever you go from aluminium, which has got oxygen in it, to alumina to aluminium. you got to do electricity to separate off that oxygen. All right, and then just one last topic that I thought I'd talk about, because I think it's interesting, and I don't know, maybe some people would be interested. I think there's some people working on different technologies around, but you don't necessarily need to do PVT, you can do PV to T. So you could just have PV modules and then turn them into thermal energy. And I think that still fits within people who have expertise in heat transfer and thermodynamics and stuff like that, which is my background. And I think one very low-hanging fruit for that is making hot water. So I have I'm managing an International Energy Agency task that a part of the task is looking at what are the best ways to turn PV electricity into hot water. And whenever we got going on it, we realized there's a lot of technologies in there, and they're all emerging. And they can solve some of the challenges that both Australia and Chile are facing. So I saw some news that there's been a lot of curtailment of PV electricity in Chile recently. And it's like many megawatt hours are being just not used from the PV because you have excess electricity during the middle of the day generated from the solar, and then you just turn it off. So it's a waste of electricity. Same thing in Australia. There's parts of Australia, the South Australia, where the price goes negative at some parts of the day. And so you actually get paid to either turn your thing off or take electricity from the grid, which is kind of funny. And so what could we do with that excess electricity? Well, a really low-hanging fruit is you could make hot water. And if you just time the usage of your hot water, time the production of your hot water to utilize that excess electricity, that's pretty valuable. So you can actually have a big positive grid impact with some of the technologies that are coming to market now. There's a few manufacturers that are developing these things. One of the technologies looks like this little box here, and it's called a PV diverter. So if you have solar on the rooftop of a house and you have a hot water tank, rather than exporting the electricity, this smart box will say, well, before you send it off to the grid, put it into your hot water collector. There's other technologies which David is working on, where you just try to time the usage of or the production of your hot water to match with when you know the grid is making solar electricity. And that works well if you have some kind of aggregated control system where you can turn on and off the hot water tanks remotely. And if you know something about the grid and something about the usage, you can still guarantee that people have hot water, and you can make sure that all that solar resource has a place to be used. So anyway, so that's technologies there. So I sort of think about it like the impact on the grid versus the distance away from the solar generation to the load. Okay, so some of these technologies, you could have hundreds of kilometers away PV generation and then still use it for hot water. And there's one last class of technology where you get them really close together and you just use the DC electricity from the PV and send it into a DC resistor in the hot water tank. And that's good for off-grid or places where the grid is maybe not reliable in rural areas far away. So that's another technology there. So anyway, I've been doing a bit of work on that kind of stuff. I think that's really interesting. One of the main reasons why I think the grid integration stuff is really interesting for kind of developed countries. And the reason I think it's really interesting is that the average household uses about 6 kilowatt hours of hot water energy per day. And there's about 1 billion hot water tanks already installed all across the world. So multiply those together, that's 6 billion kilowatt hours of energy storage capacity that's already installed. So that's going to be way cheaper than buying batteries, doing some fancy phase change thermal storage or anything. These hot water tanks are already there. We just got to figure out some smart systems to use them. So anyway, so that's the other kind of PV to T technology that I work on. And people always forget about hot water whenever they make building energy efficiency codes and standards and regulations and even incentives. Hot water systems always get left off, but it's a huge thing. Also in Australia, I don't know if it's the same here. If you export your electricity onto the grid, you get a lot less than what you get if you buy it from the grid. So your selling price is way lower than the buying price, so might as well use it in your house. Okay, so anyways, that's a few technologies that I've been working on recently. And I guess just thank you for coming on the last minute to my talk. And if you have any questions, I'll be happy to answer them. Yeah. Yep.
What was the ideal temperature between the PV efficiency system and the thermal?
So let me go back to that graph. So that's a good question. So there. Yeah, so the PV, the way that they do this testing of PV, they tested at 25 degrees Celsius under one sun, one AM 1.5 spectrum. And anything above 25 degrees Celsius, the efficiency goes down about, you could say half a percent per degree Celsius. So it just goes down, 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 down. So the best thing you can do is keep it as cool as possible. And then I guess a lot of my work is to try to split the spectrum one way or another so that the PV is far away from your hot thermal collector. And at least then you're close to the normal temperature. But actually, if you do something where you remove some of the sunlight that would normally turn to heat, if you remove that, it could be operating cooler. But it's probably still going to be above 25 degrees Celsius. I mean, if it's 30 degrees outside, that's the temperature you're going to have on your PV, and probably more. A PV just in the sun can get to 50 degrees Celsius. Yeah. And then the thermal part, so the thermal collectors, I mean, the efficiency and certainly the cost goes up and up and up as you try to get to higher temperature. So the low-hanging fruit for thermal part is the lower temperature, the cheaper and the easier. As you get up to 150, maybe you can do things like I was showing with these special little concentrators that don't require tracking too much, the CPCs. But if you go above 150, you got to start adding in, you know, some kind of serious concentrations and tracking and stuff like that. So if you want to do that aluminium processing thing, that's 700 Celsius. That's big scale stuff usually to be economically viable. But the lower end is possibly achievable without too much cost. Yeah.
Question about the nanofluids. It's nanoparticles coated with silicon. I wonder, because I've seen a lot of studies that for like this portion of particles to treat cancer, for example. And it's like the opposite, like silica core with a
Gold
shell or
yeah.
what they're like, you guys, what was the challenges or
Yeah. So it's the same idea, I guess. So for cancer treatments, I have a bit of work on that too. What you want to do for those is just absorb in that therapeutic window, which is a bit longer wavelength, and you don't really care about the other stuff. So there's many ways you can make that. Rods, gold rods, yeah, maybe some core shell particles give you that absorption, high absorption in that little window. And basically the window is where your skin transmits the infrared light. And so that's usually what they're trying to do there. So our objective was a little bit different. We were trying to absorb some short wavelength and some long wavelength. So we had to come up with a little bit different design. So we ended up using silver, which you wouldn't use in the body. Silver's a little bit toxic in the body. Gold is a nice noble metal. But silver and the discs of silver really make these kind of sharp peaks where you can have really well controlled optical properties. Anyway, just different design objective, I guess. But yeah, there's a lot of things you can do with nano materials in terms of optics. A lot of people focus on nanomaterials for maybe some thermal purposes or chemical purposes, but optics is an interesting kind of, I think not too many people looking at it. So yeah, there's a lot of innovation there. Yeah, and gold is more expensive than silver probably, so we wouldn't want it for our trying to make low cost. Silver's still a little bit expensive, but oh, I forgot to say, for these things, it's definitely less than 1%. Something like 0.2% concentration is enough to give you the properties. So you don't need very much. It's 0.2% by volume of particles to fluid. Yeah. In the back.
Chile and Australia have some similarity, like getting more solar power, solar energy to generate solar power, as well as Nordic countries have lot of lithium sources.
Lithium sources? Yeah, yeah.
Australia, they have any making this storage system coupling solar energy with lithium, using lithium. They have any proposal or doing any kind of work to storage that energy.
Yeah, so yeah, you're right. I mean, we in any way, we don't have that kind of manufacturing in Australia to make the lithium batteries, because that needs large scale gigafactories and things that are going to be in China probably. Yeah, so you lose something. You can definitely buy batteries, but I think thermal storage, the advantage of thermal storage, one of the reasons I've looked at that is it's way cheaper per megawatt hour. You know, and certainly like those hot water tanks that are already installed everywhere, that's already there, than buying lithium ion batteries. So yeah, I guess Australia is mostly focused now on producing hydrogen, which is something that could be stored. There's also some work at my university on flow batteries, which uses vanadium oxide flow batteries. I don't know if you know about those. And that's good for large scale stationary storage. But yeah, I think the world's supposed to run out of lithium if we make as many electric vehicles as we're supposed to make and all that. There's a lot of challenges with that. I don't work directly on that. But yeah, I think that's a challenge. Definitely that's the problem. I mean, renewable energies, they come when they come. You can't control them. On our whole society likes to use energy right when we want it. If I turn off this computer, I expect the grid to manage. If I turn on all the lights, I expect the grid to instantly give me the electricity that I need. So we've gotten used to being able to have energy right when we want it. And solar and wind and all these renewables don't necessarily cooperate. So the answer is some storage, for sure. And then it's just a matter of what kind of storage makes the most sense for your economy and for your region, and trying to balance those things. I don't know if batteries are going to be the big answer for, especially lithium ion. I don't think that's cost effective. It may costs are going down quickly, but some other options are going to be in the mix for sure. Yeah.
It's okay. And maybe like you did none of it, maybe it feels like more traditional, like silver and silicon oxide. And do you have tried with any other advanced technology like graphene?
Yeah, I have some one recent paper from this year where we were where we were using quantum dots, carbon quantum dots, and that one was for low temperature applications, so like down very close to freezing for like refrigeration. I can give you the details of that paper if you want to have a look. Yeah.
Okay, maybe it's okay. And use cadmium telluride as a PVC. What is it tried for the traditional silicon based?
Okay, so that's sort of the innovative, where is it? It's back towards the end. I guess the innovative thing for that one is we wanted to transmit the light through the PV module. So I've done all kinds of PVT technologies, right? One of them is just a thin film, and then you have a reflector. So that's kind of like the same thing. So it's transmitting the light through the thin film and off the reflector bouncing. This one, we had the concentrator, and we just wanted something that was mostly transparent that could go through. I think there are silicon modules which have some semi-transparent silicon where you cut the wafer really, really thin. But you need a certain path length in the silicon to absorb the photons. So it's not a good choice for transmitting usually. It does transmit infrared, but with the back contacts and all the other parts of the silicon modules, it's not necessarily the best choice for what we were doing. But the cadmium telluride, is there a good picture of it? Anyway, it looks like a glass window almost. It's very transparent. You wouldn't even know it was a PV cell by looking at it. Yeah. Okay, in the front.
Thank
Yeah.
you, Robert. I have two questions. One is which of these prototypes have the best efficiency combined PVT efficiency? And the other one is considering all the products that you can sell, the co-products, which is we have the best levelized cost, and considering these incomes, have you that?
Okay, so the first question, so the best efficiency I'd say was this system had a pretty good efficiency because we got pretty good control. Where's the picture? There. We got pretty good control of the nanofluid properties, and we got high thermal efficiency. We operate this one, by the way, at lower temperature. Especially if we're using water, we keep it below 100 Celsius. And so that makes the thermal efficiency higher. And then the PV can be pretty high efficiency. So that was probably the best. So probably the overall combined efficiency was close to 50%, something like that. And then the second question. Yeah, so these again, probably got to go back to these. I have several papers on this, some more recent one than that one. But anyway, we did the fluids, the nanofluids, even though it's silver and you'd think it would be expensive, it's $1 per liter. And then of course it's a closed loop, so it's not like you're throwing it out. You just you use a heat exchanger. $1 per liter for that. If you could use regular PV, which I hope to do in the next one, that's 20 cents, less than $1 per watt, definitely. And then if you don't try to make too much concentration, I think that can be, the concentration system could be like $1 or $2 per watt. So anyway, for this nanofluid collector, one of the papers, I don't remember the number, it did figure out the levelized cost of heat and the levelized cost of electricity. And then I guess you could sort of like add those together. One trouble, of course, is the thermal energy is not all the same, right? So you can't just add, electricity is beautiful, 100% available energy. 100-degree water is much less on the thermodynamic scale. So what we do is we kind of use like a Carnot efficiency to kind of rate the thermal output relative to electricity. So there's a thing called a merit function that we kind of propose. But anyway, it's not so straightforward adding up the thermal and electrical. But there is some analysis of economic analysis in some of the papers, if you want more detail. I don't know the numbers right now, but yeah. Yeah. Okay, in the back.
So you take the PVT concept that we have.
Yep.
The three types. So you take the energy output from the solar cell, right?
Yep.
Like, say, like the fluid heats up, right? So
Yep.
What is the economics of that product? Because you sell the energy, right? Or you.
Yeah. So the economics of the heat is you're offsetting buying gas. or offsetting using some electricity to generate that heat. So then you got to know, I guess, the price. That's a very interesting question, actually. So in some places, I don't know what it's like here. There are places where heat or gas costs more per megajoule than electricity costs per megajoule. And then, but most places in the world, electricity is more expensive than gas. So that's called the spark ratio. But anyway, yeah, basically you can figure out how many watts or how many megajoules you produced from this system, and then see how much it costs to buy the gas or the other fuel, and that's where you get the value. And then electricity, if you're making it on your rooftop, you basically offset the price of the electricity you would have bought from the grid. And so that's how we do the economic analysis usually.
And when you use the aluminum project,
Yeah, it's the same thing. I mean, they would be putting gas in. Yeah, I guess our kind of basic concept for this is probably these processes are massive, you know, like Rio Tinto or Alcoa. Alcoa is the big company that makes aluminum. They just have a huge energy demand. Probably we're not going to offset all of it, but if you could take some small, you know, like if the stream of the flow of the product is going like this, and we take a cut out of there, use solar energy, you know, maybe someday you could get a few percentage of their flow through a solar receiver. When there's sun, you just run some of the flow through this thing, let's say, and then instead of using gas to process that, use the solar, and then they're saving some gas. And I think there's value beyond just the energy savings. There's a value that these companies can say we're going towards being a sustainable company, and they can get some, you know, kind of social license to be operating these energy intensive processes if they're at least trying to kind of be more sustainable. And they also you could save some carbon emissions, right? And if there's a value for carbon, I don't know if there's a carbon price here, but some countries in the world have carbon tax basically, or cap and trade or something, where they could get some value out of that as well. Yeah. Yep.
Actually, I just want to know if there are another projects about like recording or recycling of PV or someone.
Yeah, lots of so I do. I've been doing a lot of projects where we're recycling waste heat, I guess. So again, for the hydrogen production, one thing that we're looking at is that the electrolyzers, especially as you start getting large scale hydrogen production, which we're planning to do in Australia, it's not 100% efficient. The electrolyzers is something like 75–80% of electricity is making hydrogen. So the other 20–25% is turning to heat. So if you can capture that heat, you could use it to make fresh water. Because hydrogen production, I don't know if you know, but just the stoichiometric water splitting, you need a lot of water per unit hydrogen, right? So something like 20 kilograms of hydrogen goes in, and then you get a lot of oxygen, which is high mass, and then only a couple units, a couple kilograms of hydrogen. So it's like 1 to 10 roughly, just for the stoichiometric thing. And then if you're going to cool, then you need water for cooling. And also you're going to purify. The water has to be very pure inside of the hydrogen electrolyzer. So you chuck away some of the water in a normal reverse osmosis. So it ends up being 40 to 50 kilograms of water for every 1 kilogram of hydrogen, which is crazy in a drought-prone country. I think this country also could, if you start making hydrogen at a massive scale, people will be upset that much water is going into making hydrogen. So anyway, so that's one project that I've got just kind of starting. Although we did have a PhD student that just finished on that. And then PV recycling is another area of my university. And there's some spin-off companies even now that have come out of our university for doing that, PV recycling. one Australian company, and one of my postdocs is now starting a company in China to recycle PV. So one of the ways you can recycle PV is you can just kind of burn it. So you burn off all the kind of like organic parts, and then after you burn it, you get back the metals and the silicon, and you get some energy out of burning the organics. Yeah.
The other question that I have, thank you for the answer. With the biomass experiment that you figure out that was more interest these other product besides the hydrogen. This product is like an e-fuel or what is like the purpose?
Yeah. No, it's a precursor for some other chemical things, making other chemical products. Don't ask, I'm not a chemical engineer, but FDCA is a valuable input for a lot of chemical processes. So I guess pharmaceutical industries and I don't know, maybe some plastics industries use that FDCA, and they pay a lot of money for that. So I think it's all well and good to make hydrogen and all this, but I think really a good use of it is solar energy. Harvesting it, especially for thermal energy, is a little bit expensive. So we should probably think about making high value outputs as much as we can. So those kind of chemical things are pretty interesting to me. Aviation, you can make anything, I guess. If you have a carbon source and you got water, you got hydrogen and oxygen, you can make any kind of combination of chemicals with solar energy. Yeah. Yeah. Okay.
Just a quick question. You went to our solar farm?
No, I'm hoping that before it gets dark, I'll be able to see the solar. Yeah. I'd like to see. Yeah, I'd like to. Yeah, I'd like to see it. Do we have time for that? Hopefully we do. Yeah, and I'd like to see. I just got here just 1 hour ago, so I'm hoping to get a tour. Yeah. Yeah.
Thank you for coming. Well, we have a good amount of people today that is very time to check that part.